Right, here is a sequence proof as opposed to a series proof. It should be a lot shorter than some of the series proofs. Certainly involves a lot less writing. So a sequence is defined by u1 equals 1. First term is 1. Un plus 1 equals 2un plus 1. So this is a sequence defined using a term-to-term rule. You could even call it an inductive definition. For all positive integer n, prove that un, the nth term, equals 2n minus 1 for all positive integer n. Right, so we need to write the conjecture out. So the Pn, the thing we're trying to prove, is that if u1 equals 1 and un plus 1 equals 2un plus 1. So if those conditions are the case for all positive integer n, then the nth term un equals 2 to the power n minus 1. So actually in this conjecture, given that there's no series, we didn't have to do anything else. But if we're doing a proof, we do need to write it out in a formal setting. So even if we've been given the question and it looks exactly the same, you still need to set the thing out like that. Right, now remember, say how we're going to prove it. So proof by the principle of mathematical induction. Mathematical induction. So it starts off as it usually does, as it nearly always does. You start with your basal case. So if n equals 1, so u1 equals 1, right? So then we can just use the formula. So does 2 to the 1 minus 1 also equal 1? It does. So that's enough to show that P1 is true. Okay, so now we take the induction on a little bit. We need to assume that the kth case is true. So if pk is true, then uk equals 2 to the k minus 1. Okay, so that's simple enough so far. Now we need to take the inductive step and we need to write an expression for pk plus 1. So we need to do this and we have a target in mind. So target for pk plus 1, pk plus 1 is going to be, well, we want it to be 2 to the k plus 1 minus 1. So that's what we want. So we're going to have to write 2 to the k plus 1. So we're going to have to write pk plus 1 in terms of this definition here, in terms of the inductive definition, which is going to be 2uk plus 1. So pk plus 1 is going to be, remember, the next term is 2 times the current term plus 1, so equals 2 uk plus 1. That must be, it's going to be 2, and uk is 2k, 2 to the k minus 1, so 2 times 2 to the power k minus 1, and then we add on that 1. So if we expand this bracket, that's 2 times 2 to the k minus 2 plus 1 equals 2 times 2 to the k minus 2 plus 1 is minus 1. Now, remember, I keep saying this, in HL maths, you will see this all the time. 2 times 2 to the k is 2 to the 1 times 2 to the k. And your basic index laws say this is 2 to the k plus 1, which is what we want, equals 2 to the power k plus 1 minus 1. And that's enough. We can stop there. And now we can conclude the proof. We've got our expression for pk plus 1, and we've shown that it's exactly what the target was. So that shows that it's true whenever pk is true. So now, since p1 is true and pk plus 1 is true, whenever pk is true, so since these conditions have been met, so our domino works, Pn is true for all positive integer z. And that is because of the principle of mathematical induction. Okay, it concludes the proof. So it was a bit different, slightly different feel to the series ones, this sequence one. I think it is easier, but maybe we just haven't practiced it as much. But you still do everything the same. You say the conjecture or the proposition that you want to prove. You say how you're going to do it. You do the base case. Then you assume the kth case is true, and then you get an expression for the k plus 1th case, kind of in terms of the first bit of information, as in how it's defined in the first place, and then you wrestle that in. Well, you use the information when you assume that pk was true, and then you turn that expression into the target. Once you've done that, conclude the proof in the usual way.